Thank you. Thanks very much. I'm going to talk to you about a collaborative project between ourselves at the Joint Research Centre and the Google Earth Engine people here. You can see the names of the main culprits on the screen there. The picture is actually Lake Maggiore, which is where we're based, and the Joint Research Centre nestles behind those mountains in the far distance, so you can see where we are. Now, surface water, why do we bother with it? Well, surface water touches every aspect of your life. It's a fundamental part of the climate system. It affects biodiversity. It affects your very cup of tea or coffee that you've drunk this morning. So the importance of it is difficult to overemphasize. The problem is that water moves. This notion of still waters is poetic, but it's not really real. Water moves all the time. Lakes contract, they expand, new ones form. 6,000 new dams built in Asia in the last 10 years. That's a lot of big new lakes. So there's a lot going on. Coastlines retreat, coastlines advance, wetlands shrink and expand, and rivers keep dancing all over the planet's surface. So it moves. Now, then we have a problem when we come to mapping it. Various of us, and Peng in the front, and myself have had a go at mapping this stuff over the years. We all come with different figures, which is one problem, and the other is that I suspect we're all wrong. We might have been right for an hour or two of finishing the map, at best. But because this stuff changes so much and so rapidly, I think that that's a real challenge for moving forward with the strong dynamic that you get from satellites. And I think Luke's just shown very much with the moving ships in that context. We turned our attention to the Landsat archive, and the first thing we have to know is it temporally and spatially consistent and rich enough to actually sustain a global mapping exercise like surface water? That graphic there represents the depth of the archive over time, the Landsat 5, 7, and 8 orthorectified scenes that are held here in Earth Engine. You can see quite clearly the three periods of the Landsat program's management, if you like. The flat bit at the beginning from the 1980s is when it was under commercial operation only. It's also slightly overemphasized because that's just Landsat 5. It doesn't have Landsat 4 in there. Then there's the big jump in 1999, partly Landsat 7's launch, partly the transition back to government management. And then the huge jump at the end with Landsat 8 and the change in the ground segment and the management there. The one anomaly that you see, that sharp drop in 2003, is when the SLC off went wrong at the end of May, and for a month, USGS stopped getting the data and then decided, what the heck, we'll get it anyway. And within a month, it was back up on track again. For us, the important thing is that whilst there is a difference from year to year, and whilst the summer months are always more heavily sampled than the winter months, everything follows the same pattern globally. So it's a good starting point for a global systematic survey. Then we turn our attention to the spatial integrity of that data set. And again, we find geospatially that there is some strong variability in it. The US, the conterminous US, is the most heavily sampled in the world. That is actually a representation of unique views. It's not just the path and row, because you have side lap between orbits, which gives you another unique observation. It does not include the end lap as you move from scene to scene, because effectively those are not unique observations. Although we do find you get slightly different radiance values because each scene is geometrically corrected independently. What is surprising is how low some of the figures are around the world. You do see variations in the picture. You'll see what I now refer to as the Helder strip, which is that bright line of images crossing the Libyan desert. That's for the calibration, where the instrument is always switched on and every scene collected. We start with that, and then we take out all the images with a solar elevation angle of less than 35 degrees, because shadow is a real beast to deal with for water detection. We then have cloud, shadow, snow, and bad pixels are taken out. The little strips along the sides of the images where all the bands aren't present, get rid of them. And that gives us our actual valid observations. And again, there's significant variation around the planet, but the worst case scenario is 13 images over Gabon, which isn't very many if you think that we've been getting one every 16 days for 30 years. That's an awful lot of cloud and bad data. Anyway, we put it all into the soup, and we produce a global surface water occurrence map. Now that image up there is literally just a map of water occurrence. Where it's dark blue, you've had water every observation throughout those 30 years. Where it's white, we have never detected water, and the purple tones in between are where water has occurred for some period of that time, but not all. This is the Dubai coastline where, of course, the coastline has artificially advanced, and so what was water is no longer water. We actually do it by treating every single image in the archive independently. Each one is treated in its own right. So this is to show you how we do it in Iran. Just one example from Iran. In the 1990s, a dam was built. I don't know if you see the dam go in there. And the dam is closed, and then the river starts to back up behind the dam, and suddenly what was a river is now a lake. So permanent water is a very difficult concept to get to grips with, but we capture that entire dynamic in the global surface water product. So the dark blue strip in the middle is where the river has been detected as water every observation over 30 years. And the paler blue is where we've got permanent water now, but it's only been there since the year 2000 when the dam was closed. And then the purple blushes at the edge are where the lake sometimes expands to fill that dimension and sometimes contracts. So the occurrence is less than in the center of the image. The heart of the beast is the Google Earth Engine capacity for uploading code and putting your code in touch immediately with the data. And we use an HSV color model, basically, and a supervised decision tree. Really, that's at the heart of it. We have 30,000 control points that we've built up, which cover the whole gamut of sediment loading and mineral deposits and depth and different water qualities, and put all that into the soup to come out with our map. We have a cloud mask, snow and ice, shadow and bare rock as well. And then what we do is to put the whole matrix in one place. So we have all 2.3 million orthorectified scenes with a sun angle greater than 35 degrees put into the soup. And we treat it as two epochs because the data density isn't enough to go forward and look at it on an annual basis. The sample was too variable if you looked at the beginning. So we first, on a pixel by pixel basis, scene by scene, we classify into water or not water, and then we sum all those water detections per month by epoch. So we have a water occurrence for January spanning 1985 to 1999, another one spanning 2000 to 2015, and then we do it over the 3 decades as well, so we've got the 30 years. We also sum the number of valid observations, and then we can create a water occurrence by month. What percentage of the valid observations was mapped as water for that month and that epoch? And then we can average that over the 12 years to create a 15-year, 15-year, 30-year, and an annual average for 2014 global water occurrence map. So those are our global surface water occurrence maps. Are you following? I'm not going to run a test or anything, but we're running out of time here. We then, because global surface water occurrence isn't the end of the story, that'll tell you the persistence with which water is in any location. But you can get the same occurrence because there's water always there, but it's only been there since that dam has been closed. Or the occurrence is there because there's water is always sometimes there. And every year there's water there, but it's not there for the full year. So you need to differentiate between permanent and seasonal water. And the way in which we do that is we set an arbitrary threshold in the Earth Engine. In this case, we use 50%. And we say if less than 50% of the valid observations that have been classified as water, if the global surface water occurrence is less than 50% in a month, it's a non-water month. That's set by us on an empirical basis. You can change it in the code. You can do what you like with it to suit your particular area. Globally, the reason we do that is because it then allows us to deal with slight variations in seasonality in terms of when the wet season occurs in one year or another year, because it can be off by 2 or 3 weeks around the planet. We do that then month by month for the 2 epochs and again for the 3 decades. And then we apply a set of 3 very simple rules down across the 12 months. If none of the months are water months, it's a dry site. You're never going to find water there. If 100% of them are water months, it's a permanent water body. Water is there for 12 months of the year. If it's less than 12 months but more than 0, we say it's a seasonal water body. So we have 3 classes: never, always, and always sometimes, the seasonal. And we do that over 3 decades, and we use that to create a global surface water seasonality. 2 products. To show you the difference between them, if we go to the Aral Sea, which is the famous permanent lake that's drying up, that's what the global surface water occurrence map looks like. These are the single scenes that go into it. So this is from 1986, and you can see the lake is full and present. Step forward until 2014, virtually all of the lake has gone. So that difference gives us that occurrence map. The purple tones are where water has been there for less time, effectively. But it's still, when it was there for a full year. So the seasonality map shows that. So you need to use the 2 products together. So you're differentiating between permanent and seasonal water. Now, another example would be here in Mopti, in the internal delta of the Niger River. You've got the same sort of global occurrence, but the seasonality is quite different. There's always water here, but not for the full year. And so what the data set does is to report these statistics on a pixel-by-pixel basis. You can go in, locate your pixel, and it'll tell you how many images were available, how many valid observations were there, how many of those were classified as water, and then from that you will get basically a probability of finding water at that location in that month. This is the 30-year summary, and at the bottom you will find water in that location every month of the year. You will always find water. In the top example, you will never find water in May, June, July, August, September. You will always find water in December, January, February. So this is becoming a very powerful tool in terms of starting to indicate the probability of finding water. It's not without its problems. This is Hong Kong, global surface water occurrence, 30-year record. We looked in that area and thought, wow, we've got a problem. We're picking up water in the city. It's urban shadowing. Then we went into the archive and looked. In 1987, it was water. And then by 2015, it isn't water anymore. It is a city. So the global surface water occurrence map was right. Thank God. We then started to look at things like river dynamics, which are another huge problem. In this case, this is a very seasonal river in Pakistan. This is at the height of the river flow. The river's at its max. A few months later, the river's in the same place, but much narrower. Jump forward a few years, and the river's in a completely different place. And again, the global surface water occurrence data set captures that whole dynamic. So it captures the expansion and the contraction and the movement of the river, and you can then determine whether the river is being managed or not by whether it flows in the same channel or not. You also get the paddy fields there as well. None of this would be any good if it wasn't validated. We built up a library of 20,000 painstakingly over many months, a validation data set of 20,000 points, which have been painstakingly checked to make sure there was water there and that the model predicts there's water there. And we do this for both areas of omission and commission. The omission points, the errors running at about 5 or 6%, and the commission at about 10 at the moment, but we're finalizing the stats now. That's the Landsat 8 sample that's been done. So you can see it's a pretty dense, globally consistent, stratified, random sample, effectively. So where are we? One of the problems we've really found is that we need a really reliable global digital elevation model at the moment. That's still an issue. Tiers not working consistently is an issue. We use the thermal data in the cloud masking, the snow masking, to pick up ice on water. We use it also for picking up the basalt lava outflow areas. So it's a problem not having that. Urban is still a minor problem, but only a very minor one. Where we really need to make a big effort is enriching the temporal sampling of the data set. And there are easy ways of doing that, like 36% of the archive's never been L1T processed. It's still sitting there in the raw format, so it can't be ingested into a mapping exercise. So that needs to be done. We need to extend the analysis to Landsat 4. At the moment, we've got it working for 5, 7, and 8, but we need to add 4 into the soup as well. And the US efforts to repatriate the archives, and as a European sitting on more than 1 million of them, we can understand the point, is a huge and important endeavor. Because we treat each individual scene separately, fusing data sets isn't such a massive challenge. And so one of the things, as soon as we have time, we're going to look at is merging Spot, DMC, CBERS data historically into the process. And of course, we've got Sentinel-1 and Sentinel-2. There's the first Sentinel-2 scene up there from last Saturday. And surprisingly enough, ISPRA was on it. That's where we work, which was a nice occurrence. So I think monthly global surface water occurrence isn't so difficult. And I'm going to finish with this one. This is a view of the Earth and the Moon from the Mars Explorer. If you're working at that resolution, where the Earth's diameter is 96 pixels or something, then global blue planet mapping isn't that difficult. But mapping when you're dealing with 2.8 million Landsat scenes, or 4 million as it should be when all the processing's done, is a huge challenge. And if it wasn't for the Earth engine, we'd still be chewing on a pencil and wondering where to go next to draw the next map of the next lake. So the collaboration has been tremendously fruitful, and we're delighted to be almost at the end. And I keep saying we're so close to publishing, but we are now. So thank you very much.
All right, thank you. I think we have some time for some questions.
So this is the second time I've seen your team present your work, and I'm very excited about it. I do flood mapping, and so I'm really interested in being able to mask out permanent, or, well, I guess permanent water doesn't exist, but seasonal water at the time of the flood, and trying to get a better sense of what is rare water and what is kind of normal for something to be there. So one, I want to know when your data will be available and how you will provide access. But second, I'm wondering if you're going to also give open access to the spectral library or to your algorithms, because I'm interested in sort of rare water, so the less than 50% occurrence per month, and I would love to kind of use your work to explore those events. So will you be making that open as well?
The answers are soon, yes, and probably. But let's expand on that. The soon, yeah, within the next two. The final stage is the validation, which is ongoing now. We've done it for Landsat 8. We need to go a little bit back into time for 7 and 5 just to check that there's no major issue in moving from one sensor to another. There's a little bit of masking still to do as well, but essentially the job is done. Noel will be able to tell us how long. I think it was 37 years of CPU time or something went into this. It was something trivial. The open access, yes, we are going to put it on an open web service which will provide you with down to that pixel level information where you will get all of the stuff I showed on the chart there. The number of observations, number of valid, whether it's classified as water or not. So you can work out your own confidence in it. If you've got 300 observations over a 15-year period, you can be pretty confident that it's a good result. If you're in Gabon and you've got 13 over 30 years, it's maybe less reliable. So all of that there. So no problem in having it available. And probably, yes, we will make the code ultimately will go available. We're still in the final stages of checking on that. But the data set for sure, and the spectral library probably too as well.
I was wondering if your model includes wetland mapping as part of open water, or is just open water body mapping?
No, we specifically exclude vegetated surfaces, so it's open water. It is open. Of course, we get most of the wetlands anyway, but it is literally an open water product. And in fact, that is one of the drivers behind that was the climate system. And you need the open water surface in order to understand the energy, gas, and water flux with the atmosphere.
Yeah. So if you were to map, I mean, if an expansion of this work is mapping, including mapping wetlands, because wetlands are a huge reservoir of water resource, having an impact for biodiversity and public health in different applications, including agriculture. Would it be difficult to take this approach, or just what is your advice for?
No, I mean, if it's a 30-meter stretch of open water, we map it. So all of the wetland ecosystems which are seasonally flooded, like the internal delta of the Niger that I showed, a lot of that is a water vegetation complex, but it's open water. It's not water. It's not mangrove which has got a closed forest canopy over it or something like that. You know, there will be things we do miss. White water. Well, if it's a 30-meter wide plus river, and we don't exclude on the basis of slope explicitly, we use the digital elevation model to build shadow masks. That's what we use it for. So we still do pick up river systems in mountain areas, yeah.
All right.
But we've never specifically looked for white water, no. There's always something new.
All right. Well, thank you very much. It's a great talk.